CCNA2, Chapter 7, Dynamic Routing. Alright, so this is where the routing starts to get fun. I prefer OSPF. We talk a lot about OSPF, the different types, and then we go over RIP. This is the only time. Which is kind of weird because they say you don't have to know RIP for the CCNA, but there's a chance you get questions on it, but this is the only time you're ever going to go after it. I don't want to read all these, so we're just going to keep going. This is very interesting, this chart right here, on the evolution of routing protocols. I suggest you guys look at it. Anyways, what do routing protocols do, right? So static routes, we could have small routes with no redundancy. It's really easy to keep up, right? But we start going to dynamic routing protocols when we want, like, I don't know, more uptime, more redundancy. This is when we start connecting more routers, is when we want this. So they discover remote networks, main up-to-date routing information. They choose the best path to a destination network. They have the ability to find a new best path, but the current path is no longer available. As for, I don't know, they have data structures. Routing protocols typically use tables or databases for operation. This is kept in the RAM. Routing protocols use various types of messages to discover neighboring routers, exchange routing information, and other tasks to learn and maintain accurate information about the network. They use algorithms, which is a finite list of steps used to accomplish the task. Routing protocols use algorithms for facilitating routing information and for best path determination. So basically all that, what they're talking about there is every routing protocol is different. Let's see what we have there. Alright, the share updates to update the best path, that kind of thing. So each one of them does it a little different, and we're going to get to where we're at. So why would we use a static route? Well, we'd use a static route in this little ammo jam here. Right, we only have 3 routes. So this route right here, this device right here, all it needs is one default route going that way, and everything's great. Okay, this one is a little more complex, right? Because we're probably doing a default route up to the internet, but then the static routes on it, we'd put in this one and this one, right? It knows everything directly connected to it. Not the internet necessarily, but it knows these 10 networks, and it knows these. If we do a default route here, this R1 knows everything because everything is connected through the stub that's not directly connected to. But this router would need static here. Then it knows these because it's directly connected, knows this one, so we need to put these in statically. So we put in 3 static routes there. Now they're nice, right? Because let's see if that's where we're going next. Why is static routing nice? Easy to implement in a small network, very secure, right? You're the only one putting it in. No one, hacker can't get into your routing protocol from 6 routers away and change the path. Route to the destination is always the same. Well, that's not true because we could load balance it, but I mean, it's usually true. No routing algorithm or update, right? So it doesn't take a lot of CPU or RAM on your device. It's just, hey, if you get this, send it there. Disadvantages. Well, if you're in a big network, they suck. The more networks you get, the more complexity you get. You have to put in all of these routes and all of these and multiple routers, and then figure out the next hops, and you have to have good documentation to do this. So if you have bad documentation, you're just up a creek. Manual intervention required to reroute. So if a link goes down, it's just down, right? We're not getting a different route at that point. So what's dynamic routing protocol use? Well, see, we have redundancy. So this is why we'd want to use dynamic routing protocols, or even bigger redundancy, right? Routing protocols can maintain all these routes. So the bigger we go, the more need we have. The more routes we have, the more need for a routing protocol we have. So when is it good? Suitable for multiple routers, usually generally independent of network size, automatically adapts to topology to reroute. Disadvantage can be more complex to implement, less secure. Route depends on the current topology, requires a more expensive router with CPU and RAM and link bandwidth. Alright. So dynamic routing operation, what's it say here? Well, we have a routing protocol. I really hate this chapter because it's so general. I like when we actually get into the OSPF, right? So it sends updates, right? And that's all it says. This routing protocol runs an algorithm, sends updates. The router sends and receives routing messages on its interfaces. The router shares the messages, routing information with other routers that are using the same protocol. Routers exchange routing information to learn about remote networks. When a router detects a topology change, the router protocol can advertise this change to other routers. So this is actually going into more advanced routes than RIP. RIP just kind of repeats routes out. Cold start. I don't know what it's saying there. Let's see what it wants for this cold start. Probably that as it starts up, the routing table is stored in the RAM, so it's not permanent. So if it changes in the when you start up, it has to be what we call converged. Once a routing protocol converged, means that everybody inside of a routing autonomous system has learned all the routes known. Okay, so I would say that's what. In this one, what are they doing here? If you look, they're not doing any routing information. They're just learning their own interfaces, right? So then we have network discovery of other routers. So the updates are sent based on what we're directly connected to. That's how almost all these routing protocols basically work like this, right? At least the IGRP ones. IGP, I mean. Anyways, so then they exchange. Just so much fun. More updates, more information, and then they converge, and converge means that we know all routes within the network, as I said before. So now we have types of routing protocols. So we have this is a great channel. So we have two primary types, right? IGPs and EGPs. Exterior gateway protocols, which is funny that they have EGPs because there's only one EGP. And then IGPs, right? Interior gateway. So typically in this, until CCNA2, and when CCNA2 before CCNA2, we never studied EGP at all. In this class, this was a CCNP topic. So we just studied IGPs, and we primarily just now study EIG, ERP, OSPF, and a very tiny bit of RIP in this chapter. And then there's this ISIS, and we don't study it. It's not even required in CCNP. It's very similar to OSPF. And then now we study BGP, which is the EGP. Okay, so there's two types of IGPs, distance vector and link state. There's one type of EGP, path vector. So BGP runs the internet. This runs things that aren't the internet, like internal gateways, and usually they feed into, I don't know, a default network. They could then feed into BGP, and some people just use BGP altogether, but it just depends what you need. So we'll just keep moving on. Oh, that's all I've been talking about. Anyway, so OSPF and ISIS, link state, RIP, and EIGRP, distance vector, and EIGRP is actually a hybrid distance vector or an advanced distance vector. So IGPs are used for routing within an autonomous system. also referred to as intra-AS routing. Companies, organizations, and even service providers use IGP for their internal networks. Exterior gateways are used to route between autonomous systems. Okay, so we can just look at this picture, and it shows you where we could use BGP, and where we could use EGP. And BGP is only used instead of a static route, a default static route, because there's redundancy. Okay, so if we have redundant ISPs or redundant links to an ISP, we use BGP instead of just a default static route like they're doing right here. Alright, so distance vector routing protocols. Well, if we break it down, it identifies how far the distance is to a network, and then it specifies the direction of the next hop of the router. So that's what a distance vector is. We're trying to figure out how far to the next hop. Alright, so link state so distance vector is kind of, I call it a Mr. Rogers routing protocol because it's all about neighbors. Okay, so it learns all of its information from neighbors, where a link state actually has like a boss and a king and a queen, I guess you could say, the DR and the backup DR that tells all information to all the routers, and all the routers have the full map, right? Whereas on the distance vector, you only know that you can get to a network because your neighbor can. Your neighbor says, hey, I have a route to this place. Do you know it? So you say, oh, now I know it because I go through you, but you don't actually know how you get there. Whereas link state builds a whole topology. And so in link state, it's almost like a complete map. Okay, so then we have classful routing protocols and classless. Classful routing protocols means that we only forward based on the classful definition. So on a class A, it'd be a /8. Class B, it'd be a /16. Class C, /24. So if you had any 192.168 address, would always just advertise a /24. So we also have classless routing protocols. So depending on the age of the routing protocol, like RIP version 1 is a classful routing protocol. IGP, which became before IGRP, which came before EIGRP, was a classful routing protocol. Classless just means that it will send the subnet mask. So classful, it just sends the network, and it says, well, we don't send the subnet mask. These are all, it's just at the class. Whereas classless actually sends a subnet because it's classless. Right, so it sends the subnet with the network, not assuming that it's a classful. Routing protocols, convergence, right? So why do we pick them? How fast they converge, the scalability, are they classful or classless, how many resources they use, and I don't know, implementation and maintenance. I don't know that we do that. Well, I guess that's installing them. So OSPF and EIGRP, they say complex, but you can get them set up pretty easy. But they can be extremely complex. RIP version 2 is awful. You have to keep small networks. Basically, all these small ones that we're going to learn today, which is just RIP version 1, RIP version 2, they suck. They're bad. Just hope you never have to use them. They're based on hop count, and they're not fun. EIGRP and OSPF are fun. Once you get used to them, they just kind of work. And I mean, yeah, you're gonna have a problem with them here and there. That's why we have to study them so much. But for the most part, they just work. Oh, so routing protocols and their metrics. So with a routing protocol, they all have different metrics, which is just how they're picking the best route is what a metric is. It just says, hey, like it says cost right here. Well, I don't like using cost because that's actually just OSPFs, but I mean, it just says like RIP uses hop count, so it says it's this many hops away, so it's close, which also is why RIP is bad, right? Because the links are different speeds, right? RIP thinks this is the fastest way, where OSPF uses bandwidth, so it takes these two T1s, and we know that two T1s are faster than 156K line. And so that's the metric, but a metric is just how it's calculating the best route for whatever routing protocol it is. So now we get to do our distance vector algorithms. What do we have here? The core of a distance vector routing protocol is the routing algorithm. The algorithm is used to calculate the best paths and then send that information to the neighbors. Okay, well, whoop-de-doo. Isn't that with all of them? But RIP primarily it cares the most about its neighbors. Remember, these distance vector are just forwarding information to their neighbors. Anyways, there's different algorithms used for each one of these. RIP uses Bellman-Forg algorithm to run its routing, whereas IGRP and EIGRP uses diffusing update algorithm or dual. If I had my choice, I'd go with dual every time over RIP. But here we are at RIP, which stands for Routing Information Protocol. It is fairly old, and RIP version 1, these are the characteristics. Alright, so one reason it is bad is it uses the limited broadcast of 255, 255, 255 and sends it every 30 seconds. It does not support VSLM, so it's classful. It does not support CIDR because it's classful. It does not support summarization because it is classful. It does not support authentication. Alright, so then we go to the version 2. They switched it to a multicast, which saves bandwidth. And why a multicast saves bandwidth is because, say we have 3 routers, a multicast actually generates one packet that goes to multiple routers. And so in the case of RIP, it's 244.009, and so 124.00.9 actually hits both this router and this router if it's sent from this router. Whereas a unicast, we'd use bandwidth crust here, bandwidth crust here. And so this broadcast, back when we did it in RIP version 1, that's what it would do. It would go out here, go out here, all the time, and waste bandwidth. And so RIP version 1 was really bad, RIP version 2 is a little better, but every 30 seconds it's sending this routing update with all of its information. Here's the other reasons it's bad. Uses hop count, right? Which doesn't mean we're using the fastest way there. Again, and then this worst part is a hop greater than 15 hops is deemed too far, meaning you can only have 15 hops away before it kills the route. So you have to keep your network small in it. That's basically what it says. It's classless, or RIP version 2 increased to classless. It was more efficient because it used multicast rather than unlimited broadcast. It supports summarization. So summarization is just like when we do a static route summarization, where we can say, hey, instead of just broadcasting out everything you have in your table, just summarize and say, if we have 4 networks that fit into one, we'll use a CIDR address and just send that out as a summarization, right? Where a subnet mask allows multiple addresses to be sent instead of 15 addresses that all fit into one. Secure supports an authentication mechanism to secure the routing table and updates between neighbors. Most of these do. RIP has this thing called the AD. Hopefully you guys remember what the AD is, and it's 120. The metrics one is hop count, and the AD is 20. Then we have EIGRP, and it has a few things it can use as a metric. By default, it uses bandwidth and delay, but it can use bandwidth, delay, load, reliability, and actually there's a second reliability for the fifth one. Its routing updates are broadcast every 90 seconds, which actually they're multicast every, oh, this is IGRP. Okay, so they were broadcast. And then we went to EIGRP, and this is where it became awesome. Bounded triggered updates. This does not send periodic updates, only routing table changes are populated whenever a change occurs. So instead of just forwarding it out all the time, just do it when there's changes. It uses hellos for keep alives, which are lightweight, and just keep the route alive, saying, hey, this router's still there, we still can see it. Then it only has to multicast when there's changes and updates. Maintains a topology table, so maintains all the routes received from neighbors, not only the best paths, right? So if the best path does go down, you can instantly have what's called a feasible successor come up, which is the backup route. So it keeps backup routes, is basically what that's saying. And rapid convergence. In most cases, it is the fastest IGP. The reason Cisco says this is EIGRP. They made it a more open standard, but most of its proprietary things about the routing protocol, most of its proprietary features are still Cisco proprietary, so Cisco's always going to tell you EIGRP is the best. So OSPF and EIGRP both can, usually you want your network to come back up within 3 seconds, and so they can use all kinds of timers to come back up within 1 to 3 seconds from a fail. Multiple network layer protocol support. EIGRP uses protocol dependent modules, which just means it usually separates between IP version 4 and IP version 6. But back when there are legacy layer 3 protocols such as IPX and AppleTalk, it was just a really neat thing to have, I guess. Alright, so how do we set up RIP? So, RIP is fairly easy to set up. And here's our reference topology, but so you guys, you know that we're going to have to put IP addresses on some routers, right? And they're going to have different IP addresses. Then we just go into configure terminal and we say router RIP. Okay, and so that takes us into router specified, RIP router specified, I guess. And by default it auto summarizes, and so we can turn off auto summary by saying no auto summary, and that stops it from just sending out. It'll summarize at a classful boundary if we don't say no auto summary, which I think we'll go over in a second. Default information originate is how we share in a default static route, so it'll be advertised throughout RIP. Now I don't know why they highlighted those right there, but we'll find out if they talk to us about it. So we do router RIP, and here's what's going to start the forwarding. We put in network 192.168.1.0 and 2.0. So we're this router, and so what this is saying is start broadcasting that we have these networks. And so once we have other routers in RIP, they'll start accepting those. So we would actually do the router RIP on all of these and say, hey, if you're in 2 and 4, so this guy would advertise that he's connected to 2 and 4. This guy advertises 1 and 2. Just think about how nice this would be if you were doing static routes. You only have to type in 2 things rather than putting, hey, this is the next hop for this network, and this network. So you'd have 3, and actually I guess this guy would put in 3 himself. But instead of having to have documentation with an accurate map of how you get somewhere, you just say with a dynamic routing protocol, you type in what you're directly connected to, and then it works. It's very, very nice. It's hard to go back to once you do it. Alright, so we can show IP protocols. It shows us information about all routing protocols, but with RIP it shows that we're sending out every 30 seconds and that our dead timer is after 180 seconds it's gonna kill it. So that's after receiving a RIP update, it would kill it, or hold it down, pull it out, and then after 240 seconds it would throw it out. I think it's going to go over that in a little bit, but basically that just means, like, since RIP is just broadcast, what happens if a far network goes down? Well, we use these hold down timers and kill timers to make sure that we don't form, or try not to form, a routing loop, which RIP is not the best at not forming routing loops. That's why it's not so great. So now, how do we turn it into version 2 instead of this crappy version 1? Well, in our router RIP, we type version 2, and that's about it, right? And then we're just hunky-dory, and we can do classful. Classless, I mean. And so how we do that is disabling this auto summarization. And so to disable our auto summarization, we say no auto summary, as I've told you before. Okay, then there's another thing we can set in this passive interface. So we want to waste as least amount of bandwidth as possible. So we do this on all routing protocols. This switch doesn't need any routing information. Routing information is for routers. So on this interface right here, we say don't send routing information, especially every 30 seconds with RIP. It's wasting a ton of bandwidth. So we say passive, which will just keep it from forwarding out. Like, we will still advertise that we're connected to that network, but it will not forward out updates out that network. And let's see. Yeah, and so why we use a passive interface, we do this from inside of RIP as well, right? Passive interface G00, because that's G00 right there. Keeps us from wasting bandwidth, keeps us from wasting resources, and it's a security risk because, I don't know, a hacker can put RIP in there and just find out all of our networks and, I don't know, DOS us or who knows what else. Propagating a default route. So in RIP, right, we have IP route 0.0.0 right here. So we want that shared within our RIP interface. So we say right here, go into our router RIP, and we say default information originate. So it'll originate any default routes we have in our routing table to the rest of our RIP autonomous system. These guys that need the routing information, it will share our default gateway to the internet. So you guys should probably try out those commands. You won't use them too often, but that's one way to do it. So now we have RIP for IP version 6. And so with all IP version 6 to forward routing information past our local area network, we have to issue this command. This is one you want to save in your noggin. IP version 6 unicast routing. That one right there is the most important. Can't do anything without it. So then we go in to our interfaces. Notice our interfaces are already programmed, have addresses on, and this is where any IP version 6 routing protocol is similar to this. And so we go in the interface instead of the router RIP. We will go in there next, but we say IP version 6 RIP AS enable. Do it the same on the other interface. And so why do we don't have to use network commands? Remember, in the other RIP we have to do networks to share, but this one they're already programmed, so it just says, hey, share this because we have set this up. And then we should go into, I guess with RIP-ng we don't have to, at all. All we have to do is tell it to advertise those RIPs. We don't even have to go into a router RIP. With OSPF and EIGRP, we do have to go into route IP version 6 router OSPF and router EIGRP IP version 6 router EIGRP. Okay. All right. Link state routing protocols. I'm not going to go over this too much because our next chapter is OSPF, and so we'll learn more. So our two link state are, we already talked about OSPF, ISIS. To program OSPF, we do router OSPF, but then we do this process ID, which is a number that doesn't matter. It's just a command to figure out what's going on. OSPF uses an algorithm, the same SPF algorithm, which is the same as what GPSs use, and it's called Dijkstra. And so what Dijkstra does is it tries to find the closest to a straight line using cost, right? So what it does is whatever speed this link is, it calculates it, and the lowest number is the closest way to a straight line, which is the fastest way to any point, and that's what Dijkstra algorithm does. With link state routing protocols, each router learns about its own directly connected networks, then it says hello to its neighbors, and builds a link state packet. Then it floods those link state packets and builds a database with a complete map of the topology based on those link state packets that were flooded. Link and link state. Well, so the reason we call it link state, right, is it only sends updates when a link goes up or down, right? So it advertises all of its stuff, but then when it sends the actual changes, it's when a link goes down. And I think that's what they're saying there. So the first part, I guess they're just saying the router learns all the links it's connected to, then it says hello, you say hello, and this is kind of facetious in this time, but if they're in the same area of a link state routing protocol and they say hello, then they form what's called an adjacency. So that's what we just saw there. Then they start building their LSP based on what they know about everything, right? So that's what you're seeing, is this router is telling, hey, this is what I know, this is the cost of everything I know and all the network about that, and then all these routers will flood it to each other. They pick what's called a DR, and then the DR is the boss and takes all the link state databases and it will notify them when anything changes. But that's what we're seeing there. Feel free to read through that. It won't be bad for the next chapter, but as there's a whole chapter on this, I'm not going to talk about too much. But why do we use a link state over a routing vector? Well, one, most of the time we probably use OSPF because, like I said, it's fast converging, and it does take maybe a little more. I really think it takes about the same resources as EIGRP, but it's an open standard as well, so you don't need a Cisco router to do it. So if you're running multiple vendor routers, OSPF is the easiest way to do it. But also, each router builds its own map, immediate flooding of link state packets, achieves faster convergence. Link state packets are sent only when there is a change in the topology. The hierarchical design is used when implementing multiple areas, so you have a great design. What are the disadvantages? Maintaining a link state database in spanning tree or in shortest path first tree requires additional memory. Calculating the SPF algorithm also requires additional CPU processing. Bandwidth can be adversely affected by link state packet flooding. Okay. using a hierarchical design and creating areas. All this means, all they're saying is we build areas. Area 0 in OSPF is known as the backbone. Everything has to connect to it. And what this does is if there's a failure in an area, it's contained in the area and you don't lose your entire network. And so it makes your network have a large uptime. That's all they're trying to say. And if we had these all in the same, also they would flood so much that it would actually, we'd have to have a lot bigger routers, and it would just get slower and slower. So we can break them up into smaller areas, which help us contain problems, and also it just it keeps the flooding smaller, and when we have to run an algorithm, it makes it run faster. Use link state protocols that use link state. Well, ISIS, OSPF, and OSPF version 3. Okay. Routing tables. So, since we have these new dynamic routing protocols, we do our show IP route. Before we only saw local, connected, static. Now we have R's and O's and E's and D's. E's are external, sorry. O's and D's. So R is for RIP, and so RIP is showing us, hopefully you remember administrative distance is trust, right? So RIP is showing us its trust, and then the next number that it shows is hop count. So this one has a hop count of 1, this one has a hop count of 2, this one has a hop count of 2, right? So our metric is going to change on all of these, where the administrative distance is going to stay the same unless we've changed it, which usually doesn't happen in CCNA content. So RIP's always going to be 120, EIGRP is going to be 90, OSPF is going to be 110, and yeah, that's some things we can count on for administrative distance, which means it's going to choose an EIGRP route before it chooses OSPF, and it's going to choose an OSPF before it chooses a RIP. So it talks about, yeah, we have directly connected neighbors. Yep, we've seen these in our table before with static routes. If we look at these routing tables, our route source tells us how we learned it: directly connected, or local, or RIP, or EIGRP, which is a D, or OSPF, which is an O, and there's several O's with OSPF. What network we learned, and how we get there, which on the other ones it's going to be a little different. Okay, so remote entries, that was our directly connected. Now here's our remote route source, where we're going, our administrative distance that we just talked about, our metric, the next hop, and then our outgoing local interface, which is, so if I'm going from this router to this one, right, so I leave here, this is the outgoing interface, this is the next hop, and this is the network I'm looking for, or the destination network. Routing table terms. Well, here's some fun ones. We have ultimate routes. An ultimate route is a routing table entry that contains either a next hop IP version for address or an exit interface. Directly connected, dynamically learned, and local routes are ultimate routes. Okay, so it can be a lot of things. Then we have a level 1 route. A level 1 route is a route with a subnet mask equal to or less than the classful mask. So we can have a level 1 ultimate route. Then we have a level 1 parent route, which is where it shows us that a route is variably subnetted. So we have multiple routes subnetted from the same classful boundary. So a parent route is at the classful boundary. Or as they say, let's see, a level 1 parent route is a level 1 network route that is subnetted. A parent route can never be an ultimate route. An ultimate route is going to be how we're actually getting there. So parent route just says, hey, it's just information in this table. Like, this is an ultimate route. It's how we get somewhere. Level 2 child route. So it's going to be coming off of this parent route. So as we can see, we had the parent route right here, and these are just terms. So, but you will be tested on them. And so it has all these children to that. The level 2 child route is a subnet of a route that is a subnet of a classful network address. So those are our routes. So what else do we have? IP version 4 route lookup. It's called a recursive route, right? When we look up a route, it's recursive, or no, it's not. Sorry. Do not have recursive routes yet. It'll be coming here. But basically what they're talking about here is when we look up a route, the route that will ultimately be chosen is that with the most bits. So whoever has the longest subnet is actually going to be the most specific route, and so it is always picked. So even though these all have the same number, which would be illegal in a routing table, but if there's options, it's going to take the longest. That's why you see that local IP address thing going, because it makes it the longest amount of bits. Because if you look, it's 32 bits. Oh yeah, we already had recursive. That was in static routes. Then we have IP version 6. It's the same as IP version 4, just with our IP version 6 addresses, right? Except that every IP version 6 address is an ultimate route. Alright, we don't see any parent routes here. It's not subnetted, doesn't say anything. So every IP version 6 address is an ultimate route. We can learn them through dynamic routing protocols or directly. Alright, there's our basic dynamic route wrap up. If you have any questions, let